All right, let's do a pole placement problem. We're gonna set the desired poles to -3 and -4, and we're gonna be given a state space system. The first thing you have to do with these pole placement problems is check to see if what you're given is controllable. So let's do that right here. It'll be C equal to B, AB, equal to B is 0, 1, AB is 0, 1, -2, -3 times 0, 1 equal to 0, 1, and -3. Okay. While you're here, you have your controllability matrix. Now you gotta check the determinant of it. That's gonna be 0 minus 1, which is -1, which is not equal to 0. Not equal to 0 determinant means we can move on because the system is controllable. If it weren't controllable, you stop here. You can't do this with a system that is not controllable. This has to be met. So it is. And while we're here, we're gonna grab the inverse of C. So C -1, where over here we had the determinant was -1, is gonna be equal to 1 over the determinant of C times, we'll flip those, -3, 0, and we'll flip those signs. And that's gonna be, this would just be -1. So let's build that matrix. It's gonna be 3, 1, 1, 0. 3, 1, 1, 0. 3, 1, 1, 0. 3, 1, 1, 0. 3, 1, 1, 0. Okay. All right, we've got our controllability check and our inverse. So let's carry on. Step 2, you're gonna think of like a perfect world. In a perfect world, these poles would just have a system that they fit right into like a glove. And that system would look like, it would just be S plus 3, S plus 4. All right, we put those poles in, got our zeros, and we can expand this out, S squared plus 7S plus 12. That's a perfect world. In the real world, an actual world, we're going to be dealing in a function of A, but we can expand it to the same form. So A squared plus 7A plus 12I. Let's grab A squared. A 0, 1, -2, -3. 0, 1, -2, -3. Let's go 0, -0, -2. 0, 1, 1, -3. -2 to 0, -3, 2, 6. -2 to 1, -2, plus 9, 7. Confirm, 0 times 0 is 0, 1 times -2 is -2. 0 times 1 is 0, 1 times -3 is -3. -2 times 0 is 0, -3 times -2 is 6. -2 times 1 is -2, -2 times -3 is 9, 7. So A squared. Is right there. And we need plus 7 times A, so let's just distribute a 7 into here. We'll go 0, 7, -14, -21. And then we'll do an identity times 12. Now we can just go straight across. -2, 0, 12, 10. -3, 7, 0, 4. 6, -14, -8, 0. 7, -14, -2. Right here. All right, so now that we've got our actual scenario, we'll go for Ackerman's formula. Ackerman's formula says that your steady state feedback gains K is going to be equal to long matrix of zeros with 1 on the end, the dimension of n, so 0 and 1, times inverse of C times actual world scenario. So that's going to be 0, 1 times C inverse and A. We can do that. We can do that right over here. C inverse right here times A was up there in pink. Put it in blue now. It's going to be 10, 4, -8, -2. So that's going to be 30 plus -8, 22. 12 minus 2, 10. 10, 0, 10. And 4 and 0. So C inverse times A right here will be 22, 10, 10, and 4. Okay. Clean that up. All right, let's do it. This is 1 by 2. This is 2 by 2. We're going to be getting 1 by 2. 0, 10, 0, 4. K is equal to 10 and 4. Okay, last thing we do is we just check to see that what we obtained from using Ackerman's formula is going to be accurate for the closed loop system. So it's going to be ACL equal to original A minus BK. So BK, we can do that right here. B is 0, 1. K is 10, 4. That's going to give us 0, 0, 10, 4. So this is going to be equal to original A, 0, 1, -2, -3, minus B times K, which is right here. 0, 0, 10, 4. Okay, let's clean that up. All right, let's go straight across here. 0, 0, 1, 0 is 1. -2 minus 10 is -12. -3 minus 4 is -7. Okay. So let's just put here so it's nice and easy. 0, 1, -12, -7. Okay. essentially we're done. But now we want to check. We want to say, does this closed loop A matrix give us the poles that we want? In order to do that, we need to do a quick eigenvalue check on this ACL here. And I suppose we'll do that in green. Okay, so eigenvalue is going to be determinant of lambda I minus A ACL set equal to 0. So let's see. Lambda 0 minus 0, 1, negative 12, negative 7. That's lambda minus 0. That's negative 1, 12. And lambda plus 7. Okay. So we'll do determinant check here. It'll be lambda minus 0 times lambda plus 7 minus negative 1 times 12. Okay. Lambda squared plus 7 lambda plus 0 lambda plus 0 plus 12 equals 0. All right. That's going to factor to lambda plus 3, lambda plus 4. Lambda 1 equals negative 3, lambda 2 equals negative 4. And sure enough, negative 3 and negative 4 is what the system became, and negative 3 and negative 4 is exactly what we wanted. And that's a pole placement problem.